Hello, everyone, and welcome. My name is Elisa Cuellar, and I am the Assistant Director for TTI UTC program. We appreciate you joining the webinar on the Developing AI-Driven Safe Navigation Tool. You all have come into the meeting muted and with your cameras disabled. If you have any questions during the presentation, please use the Q&A option at the bottom of your Zoom window or the chat feature. We will address those questions either during the presentation or during the Q&A session. If you would rather ask your question yourself, we highly encourage that you just ask and you please raise your hand and let me know via the chat, and I will unmute your mic and or video during the Q&A so you could discuss with the presenter. We encourage the conversation. You should feel comfortable to do so. Captions will be on for your convenience. At this time, I'd like to introduce you the presenters today. Dr. Subasish currently serves as part-time associate research scientist at the Texas A&M Transportation Institute. Beginning in 2022, he joined civil engineering program at Ingram School of Engineering, Texas State University as an assistant professor. Dr. Doss has over 15 years of professional experience in fields such as roadway safety, traffic operations, connected and automated vehicle technologies. His body of work includes the publication of more than 200 technical reports and journal articles. In addition to his research endeavors, Dr. Doss is the author of the book Artificial Intelligence and Highway Safety, which was released in 2022. Dr. Doss actively engages in professional organizations holding memberships in ITE and ASCE, and is distinguished as an Inno Fellow for his contributions to the field of transportation. I will now hand it off to you, Dr. Doss, for your presentation.
Thank you, Lisa. So I'll share my screen.
Yes, please.
Can you see the full screen?
Yes, we can see it. Thank you.
Hello, everyone. I'm Subasish Dash. I'm an assistant professor at Texas State University. I joined there in 2022. Previously, I worked at Texas A&M Transportation Institute. Today, I'm going to present the recently completed UTC project, Developing AI-Driven Safe Navigation Tool. And in the next 40 minutes, I will explore different works done in this particular project. So here's the outline of today's presentation. So at first, we'll give introduction and what are the research problem, what are the current research gap, then the methodology, key finding, and conclusion, as well as future direction. So what is navigation? Navigation has started long back. So it has started with seafaring and later extended to land, aeronautics, and space navigation. And in the previously, it was done by dead reckoning or celestial navigation, which means that you know a location and then you move to another location. So what are the distance and what are the directions from the original locations? In that way, people have started to navigate. When roadway signage started to kind of become apparent, the navigation system became very important for the drivers. And in 1910, we'll say that the first rolling map was basically introduced to the drivers that can help them to navigate from one location to another location. Since 1960, there are basically route guidance systems that are basically started to help the drivers to kind of go from or move from one location to another locations. And currently, we all are familiar with different navigation tools. Majority of the time, it is either in a GPS or mostly in our cell phones. We have Google Maps, Apple Maps, Waze, MapQuest, in different forms that basically give us two major things. One is basically the fastest distance, another is basically shortest distance. So based on the preference of the user, you can go to from location A to location B, either by choosing shortest or fastest navigation. But one of the caveat is there currently exists that we know shortest and fastest, but there is no tool that provides us real and dynamic kind of route selection based on safety. So there is a research need to accomplish that. So again, there are some also caveats in the kind of fastest route selection and shortest route selection. In many of the cases in fastest route, we'll see that you need to basically enter into the freeway, and then most probably for the shortest distance period, you need to again exit it. So it is kind of sometimes nuisance and disruption. On the other hand, in the shortest path, you'll see that maybe narrow lane, there is lack of lighting and other geometric difficulties which are not apparently safe. So there is kind of a need that can provide us guidance based on the safety scores, and that safety score should be in real time by collecting data from multiple sources. So this particular project is aiming to mitigate the research gap by introducing a framework and a kind of tool that can show us how AI-driven different algorithm can help by getting the data from multi-source data fusion and can give us some safe routing scores. We conducted a comprehensive literature review on this project. When we started the project, Soil Sorabi and Yanmo Wang was with us. So they basically helped me in developing a kind of a comprehensive literature review. And we also published the literature review in a accident analysis and prevention journal that provides kind of an overall approach of what are the state-of-art safe routing tools, mechanism, algorithms, different data sets. So here we are just providing a little bit of glimpse of the literature review that we provided in that AAP paper and also in our final report. So we found that the route selection have kind of different sections to see how you can define your risks. It can be crime risks, it can be health related risks, like for example, the bicyclists and pedestrians when they work in a city locations, so they want to avoid where basically air pollution is higher. So health risks is a kind of route selection important parameter. Then there are other conventional safety like vehicle crash, pedestrian or bicyclist crash, hazmat related kind of risks, and also kind of some other kind of different risk measures that are basically defined by the users. And when we basically consider the safety consideration for vehicles, pedestrians, and cyclists and public transport, we need to consider different sort of factors like crash severity, walkability measures, lighting condition, precipitation or weather or kind of glare related information. So that can basically help to define a personalized version of road safety. And we also found that in the literature that researchers use different methods. There are some methods that basically use deep reinforced learning method to find the efficient route based on kind of different factors that we described earlier, like health risks, crime risks, then kind of crash-related vehicle or pedestrian or non-motorist crash, vehicular speed, posted speed limit, and other roadway condition. And when the algorithm to give us the kind of routing, kind of either based on shortest or fastest, there are kind of different algorithm approach were used, like predictive versus reactive approach, static versus dynamic approach, and centralized versus decentralized algorithm. We'll basically go through some of those kind of algorithms in our next slide. So what is predictive and what is reactive algorithms? So kind of reactive is observational data. We collect the information from the observational data and we score risks. On the other hand, predicted is not only we are taking the observational data, we are basically also kind of, so when we are saying about observational data is basically either incident or crash, but there are other information like roadway features and other conditions like traffic volume and weather condition, posted speed limit associated with different operating speed measures to be considered there. And then we can predict the crash risks on those segments, either long-term or short-term. So when we say long-term, that means that we collect the data at multiple years and define safety score or risk score on a segment on a kind of extended period of time, but we can basically make our prediction model short duration by basically temporarily segment the time frame, like by year, weekday versus weekend, or we can do also by kind of different season and the kind of time of the day. The second form of algorithm is known as static or dynamic algorithm. So this algorithm can provide whether you have the information is kind of a static in nature or real time in nature, and from them when there is kind of static in nature, maybe you can upload the system or the tool in an online platform, and then it does not need any data streaming mechanism. But when you want to do the real time, then your mechanism should be, it should have process to kind of have newer data and update the model. So which is basically more critical. There are other two algorithms. You see that it is kind of centralized versus decentralized. Centralized indicate that it is basically think about the holistic approach, like all users. On the other hand, decentralized mechanism is basically for individual users can make their decision to maximize their own benefit. So to get the safe routing in the conventional literature, what we found that safe routing algorithm guide the users to provide information on safety on the different routes, and then the user can select which route they prefer based on their personal preference or based on their need. It may be shortest time, it may be fastest time, or it may be safest route selection. So it basically relies on mostly historical data to estimate the crash risks. But again, we need to emphasize that if we develop a model for a certain years, then if there is a newer data or newer information, that cannot be updated in the static nature of the tool. So safe routing should consider the different changing factors, like for example, in a route, the traffic volume are continuously changing, operating speed measures are changing based on the posted speed limit. If the posted speed limit is changed, operating speed will change. So far, it will change the overall safety score. So there is a need for dynamic predictive algorithm that can provide real-time crash predictions. So to develop a safe and robust navigation tool, we need to collect information from multiple sources, and some of the key variables there are important, like travel time or operating speed, and then traffic volume is a very important measures, and then incidents also are vital. The conventional crash dataset, we have all of the crash related information, but we do not have kind of incident information. So we need to collect incident information from different kind of vendor data. Like for example, Ujo is a company, they sell connected vehicle data, and they also sell kind of safety events data. So those data can be used to get the real-time dynamic tool. And then there are kind of other kind of databases, vendor database, then OpenStreetMap that has kind of different rate of pedestrian bicyclist facility information, traffic sign information, and here provides posted speed limit information. And then there are other multiple open source data set can be used to provide a more dynamic nature of the data set that can be used in defining a real-time safety navigation and associated risk scores on different routes. In this particular kind of figure, we are just showing that how the static route finding and how dynamic route finding differ. So we know that we have the roadway network characteristics. We need to understand here that the characteristics of roadway networks is also kind of static in nature for a certain period of time. But if we think about a 5-year period, the roadway network characteristics also change every year to some extent. So we have the intersection characteristics, we have the kind of roadway characteristics. For example, intersection characteristics, it may happen that previously in an intersection there are a stop sign, but in 2018, but in 2021 there is a kind of signalized intersection. So that basically changed the safety score. So that's why we are kind of continuously mentioning that in the safe navigation to development, we need to think about the static versus dynamic nature, and dynamic nature of the tool requires more real-time data from multiple sources, and there is no current platform that can provide this sort of multiple data source fusion altogether to give you a real dynamic safety score. So on the right-hand side, we showed kind of the other information like aggregated traffic measures and historical crash data. Again, historical crash data, it will definitely be changed every day. So kind of if we collect the data and develop the model after capping the years, like for example, develop a model 2017 and 2022 data set for 5 years, versus when you have a dynamic tool, you need newer data incorporate in the crash data set regularly, and it will update the model. On the other hand, aggregated kind of traffic measure that can be also kind of historical. It can be if we cap it with certain year, that will provide us a kind of a capped version of traffic measure like operating speed limit or standard deviation of operating speed, average travel time, and then there are kind of other kind of travel measures that we can use to determine those things. On the other hand, there are the red color the icons show those measures that are kind of real time. So real time traffic measures, real time road incidents, and kind of weather condition in the real time. So if you can incorporate the real time information like real time traffic measure, real time incidents, as well as kind of real time weather condition, the dynamic route finding can give us more robust and safe route algorithm based scoring. So what we did in our particular project, so we developed a framework that kind of showed the overall mechanism, how you can develop a safe routing tool in both static and dynamic nature. Currently the tool we developed is basically we kept the data in a certain year, so it is kind of a static in nature, but we provided the mechanism how there will be the newer source of data can be incorporated in the tool, and it can update the models, and the tool can be dynamic. So for this particular project, we use kind of Texas data and use Texas as a test bed. So we use basically 5 years of crash data from 2017 to 2021. And this crash data set have nearly 172 data fields. And to get the route information, we need to basically provide safety scores on all of the roadway segments, and we need latitude and longitude of the kind of those crash locations. Texas data is well populated with that long, and we found that in 2021 crash data, we have around 98.25% of the data we have latitude and longitude. So that is kind of a very higher percentage, and we just missed a little bit of 1% or over 1% of data that does not have any lat long. So here is kind of an overall kind of distribution of caches over the 5-year period. And then we showed also kind of in the second row to show that the amount of data that has kind of lat and long. And we found that in the previous years, like 2017, 18, we have higher number of missing. But if we take a look at in 2019, 20, and 21, basically Texas is kind of, the database has a lot of less missing information on lat and long, and provides more impact on getting kind of historical observed crash information to be assigned to the routes. And in the bottom, we showed the number of variables that are in the crash data set, and we see that over the year, there are slight increase of total number of variables. So we need a roadway network. We used Rhino as our roadway network, and Rhino is a roadway network provided by Texas DOT. They every year update the network, and for this particular work, we use 2021 version of the Rhino, and it has nearly 514,480 roadway segments. So here we are just showing that how many total records, how many fields there, what are the primary key, and location of the data, classification of the data, and other information. So we also used weather information from NLDS, that is North American Land Data Assimilation System. So that provides very high quality weather information in the form of precipitation, wind speed, temperature, and this data are in basically raster format. So we can basically, when we conflate our data, the roadway network with the raster data, we can get on the same segment different short version of the segments with different precipitation measures. And then when we calculate our overall safety scores, we basically get a weighted score on the segment in different duration of the day. Like for example, we started the data with 10-minute interval. Then basically when we develop the model, we compile all of the information at the hour level. And then from there, we basically predict our safety scores based on all of the information from geometric feature, crash information, operating speed data, traffic volume data, as well as precipitation information to get an overall safety score. So NLDS dataset is kind of better than airport weather station data. As I mentioned that in the majority of the time, airport weather station data is a single point data. So you can basically conflate your single point to kind of an area with 5 mile, 10 mile radius, but it is kind of oversimplification of the information. On the other hand, NLDS basically get information not only from airport weather centers, it basically collect information from different sources, including roadway weather information system, and it can provide a conflated version or raster information of precipitation on the overall area, and then we can basically use the data for our granular uses of weather information on roadway segments. Just show few variables that are basically to give a overall glimpse of the NLDS. So we get the 10-minute data, but we convert it to 1 hour for our modeling purpose. So the other rows indicates what are the ranges and what are the kind of GS locations, time of the day, and source of the data. So again, in this particular project, we needed to do extensive work on data collection, data fusion, and then after collecting all of the information, we needed to do use the different AI algorithms to see which one is giving us best predicted measures. At the same time, we need to, when we develop our tool, we need to provide information about safest and fastest route selection algorithm. So we experimented with different algorithms. In these slides, we'll explain some of these algorithms that we explored so far in our current projects. So we basically, in our final analysis, we used Google Directions API, the shortest path algorithm that basically used 2-graph algorithm, Dijerker's algorithm, and A-star algorithm. And we use the API to real-time calculate the shortest route from based on our origin and destination. Dijerker's algorithm is one of the popular algorithm that is used. It basically provide single source shortest path problem in the assigned graph. And this algorithm takes out the least distance of the unvisited nodes for each time and update the distance of the other nodes with that node to give us the shortest route. A-star uses an approach called Manhattan distance. So Manhattan distance is not point-to-point direct distance. It is one point to another point. It will have a right angle. So it is called block, Manhattan block. So if you want to go from one location to another location, you need to go to the intersections to another block, and then you need to go perpendicular. So it uses similar thing. So it is considered as one of the best first very pretty first algorithm, and that basically use is cell in the convolutional space that are evaluated based on the Manhattan distance of the cell. And then finally, it gives us the shortest route based on the overall mechanism. So we are not basically going through all of the in-depth exploration. We are just giving you the brief idea that how these algorithms work. Then we also explored what are the other algorithms, like there are Open Route Service has an API of shortest path. This algorithm is intended to minimize the travel time rather than travel distance, and the mode of transportation selected by the users, and sometimes it can give additional filter to choose your path. There are other 2 algorithms we have examined, but again, we mentioned that in our final tool design, we used Google's API that basically use either A-star or Dijerker's algorithm. So ORS API is another API that uses CS algorithm to calculate the shortest travel time route. And using this algorithm, route can be categorized by different level, and then it can basically provide the highest level to lowest level, like different facility types to being considered how to get the shortest path. There's other one we explored, it's called core alt algorithm, when it is desirable to avoid obstructions such as rush hour traffic, jams, traffic accidents, and roads, then there are higher safety risks to drive on. So in many cases, that algorithm we can use. One of the difficulties of applying this algorithm, we basically tried to experiment with this algorithm, but the whole code is not open source at the time. So we kind of failed to test this algorithm in our analysis. So again, in our overall tool development, there are kind of three major things we needed to take care. We need to collect multi-source data. We need to do data fusion so that the data at different temporal level and different different temporal levels, so that we can basically, when we select the kind of tool that can basically develop the model of shortest path and safest path based on basically that temporal stamp in the data. So to get our risk scoring, we needed to use AI algorithms. So we tried with 4 different algorithms: random forest algorithm, gradient boosting, support vector regression, and cat boost. So one of the things we want to mention here, that we overall score risk score on the segment. So we collected the information in the form of historical crash data, and then on the road segment we assign different information like operating speed, annual average daily traffic, or kind of traffic volume measure, and kind of roadway characteristics, as well as kind of real-time weather information to get the overall safety score. And then we tried these 4 different algorithms to determine which algorithm can provide us more robust and good prediction. In our analysis, we found that cat boost algorithm outperformed than the other 3 algorithms in terms of overall predictive accuracy and overall performance. And the tool we developed, it basically we used the outcome from cat boost algorithm predicted value. Here is a kind of brief introduction of cat boost, how it works. So it is kind of based on the gradient boost algorithm. It has kind of the algorithm is refined from gradient boosting by kind of have the capability of handling missing data and numerical features. It can use both ordered boosting and random permutations to perform the analysis, and it reduce overfitting and improve the overall predictive performance. And also we found that in cat boost has another advantage is that it automatically balances different classes and select the learning rate or best learning rate to go to the prediction accuracy. The safe routing tool we developed, again, it is based on Texas, and it has an interface that provides drop-down panel, like you can want what are the kind of locations you want to use, or which one you want to select. Are you wanting to select shortest path, fastest path, and safest path? And the user-friendly design give a kind of comprehensive overview of the trade-off between different routes. So kind of if you select kind of from point A to point B, it will give you option that, okay, route 1, what are the kind of overall performance in terms of safety, what is the route 2, and then user can select the best one. So by presenting both visual representation of the safe route and a detailed tabulation of relevant metrics, user can make informed decisions that balance their priorities regarding travel time and safety. So here's the kind of overall mechanism. So we collected information from 3 major sources. We collected information from roadway inventory and crash data. We collected precipitation information, weather-related information from NLDS, and then we basically conflict the information on the roadway inventory. And then when we have the roadway inventory data with weather information, we basically assign the crashes on the segment. So again, we develop our database in different temporal segments so that we can use the data based on the time of uses of the tool. And finally, we have the data at both annual level and kind of shortest temporal level that we did basically at our level to get safety scores for each of the segments. So we basically developed our scoring mechanism first, then we used an interface, and then we basically have a beta version of the tool that can be used for exploration. So here's the overall look of the tool. So it has kind of a mapping interface, and then you can determine your temporal scope, either annual or maybe hour. And then when we are basically using annual, you can select basically all years versus kind of last 2 years, last 1 year, last 4 years, those sort of thing. And then you need to manually put your origin and destination. And when you put your information there and you hit the direction button, then it will provide you kind of the first route versus safe route, and it will give you the overall score. So we'll see here, like, for example, if we kind of select a location, NASA Houston to University of Houston, and then we find that crash score for the first route, it's 8.65. On the other hand, safe route, it is 6.88. And we are seeing that the average crash score is 0.07 versus 0.06. And highest crash score for one of the segment is 0.39 versus in safe route is 0.30. And we also provide which segment that basically coming with the highest score. There is a segment ID 8117 in first route. On the other hand, safe route is different. And sum of precipitation, it is not overall changed in the route. So it's kind of the similar. And then we provided also the distance. We are seeing that for the first route, the distance is 23.27, but on the safe route is 23.39, slightly increased. And basically the duration also slightly higher. But based on the average crash score, the user can then select the safe route and basically travel that route. So that's the overall mechanism of our framework. So I want to reiterate again here that this tool we developed from this UTC project is kind of a framework version of the tool, and they are kind of static in nature, but it has the adaptability to be a dynamic tool when we can get more robust information from other data sources like kind of Ujo data for the whole Texas for certain number of years. And then there is a future influx or continuous influx of data. Then the tool can be updated with all of those newer information. So again, the analysis of the tool we did here, it has some limitations due to the large variability in the roadway segment lengths. So it is very, very important to acknowledge that there might be some localized cluster of high risk area. Like, for example, in our tool, we created the mechanism that can provide us more information about where the kind of throughout the point A to point B, if there are kind of 20 segments, which of the segment is basically with the highest risk score. So that mechanism can be also kind of getting implemented in a more dynamic version of the tool, but we already have the mechanism. But when we have the dynamic version of the tool, that can real-time adapt this location. So there should be some clusters that are high risk locations. The algorithm can itself, without doing the calculation, it can avoid those locations. So that's the overall kind of mechanism of avoiding some of the clusters or some of the locations. But we created the mechanism in our tool that can provide us the segments, and the segments can be determined by some sort of clustering. So future research should consider kind of also another important thing is that in some of the locations we find that our roadway segment differs from 0.1 mile, it goes up to 23, 24 miles. So in some of the longer segments, we did not resegmented our segments based on the safe scoring. We basically kind of the Rhino segments we have utilized, but in future version of the tool, if we can kind of more homogeneous segments throughout the network, it can be helpful to kind of run the algorithm more robustly and get information collected in a more faster pace. Another important thing is that, as I mentioned, the tool, whether it is a kind of a static type of tool or dynamic version of the tool, it depends on the real-time data influx in the tool. So accessing real-time data on traffic, roadway incidents, and weather are basically very crucial for dynamic and predictive algorithms in real-time routing. And we know that limited public accessibility to real-time data sometimes pose challenge for even companies like Google or Apple. They cannot provide the safe route based tool due to the unavailability of some of the data for the whole network, when we are basically telling about whole network is the whole US. As part of the work we did in this project, we basically did not develop the tool for the whole US. We limited our network to only Texas based, but we have not limited by facility type or functional classification. It's the whole Texas. That is also a lot. But when basically kind of the robust kind of apps like Google Map or Apple Map are going to basically incorporate safety information in their tool, they need a kind of holistic approach so that they can get all of the real-time data from multiple sources that can provide not only the real-time observational traffic state of the road, but it can also give you information about the kind of historical context and real-time context, that there are some events in the upstream or downstreams, and how you basically select your route and basically emphasis on safety. So one of the other findings, we found that crowdsourced data presents a potential alternative for obtaining real-time information. That is kind of one of the findings from our analysis, and it offers a solution to address the challenges of kind of how we collect this data, and then kind of for the whole network level, kind of, and in a continuous flow that basically need to be explored. And again, one of the things we did not experiment with this project is that the user friendliness or user perspective, whether they like the safest or fastest route, and what are their basically preferences based on kind of either shortest path, fastest path, or safest path, and to get those information to basically incorporate in the tool. So again, I mentioned that existing navigation maps as well as all of the apps in the smartphone that basically lack real-time risk scoring. So there is a need, robust need, and the current work we did in this UTC project, it can provide the framework and kind of the mechanism and kind of a tool that other users can improve upon with the dynamic nature of the newer data. And also kind of we need to limit it to the certain data points of certain factors in our algorithm. But if there is kind of the whole framework can be reiterated or make it more robust, we need newer source of data and kind of more faster algorithms. So there is a need for continuous advancement of the framework we have developed so far to make it more real-time, dynamic, safe navigation tool. So what are the future research need from this particular project? So one of the things is that there are kind of, when we explored our kind of in the literature review section, we found one thing is that there is a need for, most probably it is called choice modeling kind of crash prediction model that basically give a more personalized vehicle level crash prediction model to tailor the trips based on individual preferences. That is one of the things. And we need to also explore more in depth kind of how the daily and hourly models can differ from the annual model, and how those can be integrated in the navigation tool. In the form that we use currently is that we basically provided the weightage based on different temporal kind of clusters. Like we mentioned that we used kind of day of the different kind of day of the week, like weekday versus weekend, different time of the day, like peak hour morning, evening peak hour, and other hours, as well as kind of different season. But it can be more kind of real-time 1 hour metrics that can give, okay, if I want to go to from point A to point B in the next 2 hours, what are the overall road safety scores on those different routes? So that part of the real-time allocation of safety scores is needed, and there are future resources needed to get that done. As well as we need to introduce newer novel methods that can assess overall safety routes by aggregating both information from the roadway segments and vehicle segments. One of the other thing I want to mention, that as we are basically in the world of generative AI, so in future there will be kind of more personalized AI. That means that if a road users has some cautions, like he's old, he does not want to use kind of interstate, or maybe toll roads or some other things, then how basically currently the app have some of the filters, but they need more personalized or based on basically historical kind of the kind of origin and destination or the preference of the route users by the road user. It can give a kind of newer weightage to the overall generative AI algorithm weightage with the personalized weightage information so that it can basically select the route in more personalized way. So again, we mentioned that currently only one caveat is that there are different data set. We can basically test the data set for a certain period of time from different companies like Ujo. They provided connected vehicle data, trajectory level data, but it is for a certain period of time. But there is a need for influx of newer data. And also kind of we need to have an understanding that whether people prefer risks as a kind of key factor or maybe travel time or distance. So distance is sometimes associated with the kind of cost of fuel. So those kind of are important parameters to make a decision making, and that overall trends, there is a need for kind of survey or similar other things to get a perception of the users to see how it can be done. So again, another important information is basically we mentioned it in the beginning that there are centralized versus decentralized safe routing algorithm. So how basically decentralized can think about kind of all users versus decentralized can think about individual users versus centralized think about all users perspective in the form of either generative AI or kind of personalized AI. So that can provide more context to the real-time safe navigation tool. So with that, I finished my presentation, and now we're open for questions.
Thank you, Subasish. If anyone has a question, feel free to raise your hand or put it in the Q&A box. Do you have any takers? Subasish, I have a question for you. How does this tool and its framework leverage prior historical data to assess and prioritize safety factors along a route?
Okay, yeah. So we mentioned that the current tool we designed, it is basically static in nature. So there is a need basically to get to the next level to make it in dynamic in nature. And to get that, we need real-time data influx continuously in our kind of data mechanism so that it can update the model with the new influx of data. So currently what we are doing, we collected data from basically major three sources. We collected data from roadway information from the Rhino. Again, I want to reiterate here, the current tool only used Texas as a case study. So we collected data from CRIS that provides all traffic crash data throughout all facilities in Texas for several years. So we collected data from 2017 to 2021. We used the 2021 roadway inventory. And then we use also kind of the raster level weather information in the form of precipitation, and then kind of incorporate everything with an AI model to give the real time to give the safety prediction in terms of safe route risk scores. So the framework is currently requires to make it to dynamic. We need kind of other information like operating speed data, roadway condition data, real-time roadway condition data, as well as kind of the event or incident information. If we can incorporate everything in our tool, that it can be a more dynamic version of the tool that can kind of be a kind of add in current popular tools such as Google Map, or Apple Maps.
Oh, thank you. I have another question here for you. In addressing the trade-off between the fastest route and the safest route, how does this tool balance the need for efficiency with the imperative of ensuring user safety?
Okay, so that is one of the limitations we mentioned. We mentioned that we have the tool that provide two interface. One is the first route, another is kind of the safe route, and it provide different scores in terms of overall risk score on those two kind of selection of routes. Like first route, what is the overall safety score versus saved route, what is the overall safety score. We provided some other additional information. Like one of the information we provided, that the segments or the segment ID that has the highest number of risk score. So that information, when basically we'll develop a more dynamic tool, can be used as a cluster, so that if we have historical information on crash or events on certain locations, then the map automatically will avoid that cluster or that basically segment of that special location. So in terms of our tool basically provide the options, but one of the things we did not explore to see that the user need, that when a user use the tool, how much they look for safety versus kind of to go to a location either by shortest distance or fastest distance, that is needed to be explored to see more a dynamic and personalized version of route selection tool.
Yeah, thank you. And I have one more question for you, Subasish. Considering the dynamic nature of road conditions and the potential real-time disruptions, how does the current project provide guidelines for the future update of safe navigation tool?
Thank you. That is a good question, basically. So we provided kind of in our report, as well as in the kind of the paper we published in Accident Analysis and Prevention about the future direction. So one of the things is that the current version of the tool is a framework, and then it has the whole mechanism. We open sourced our code and data set in the Dataverse, and it can be upgraded and kind of it can be used to have the incorporation of the dynamic nature of the data influx. Like, for example, that we collected some information in the real time from different data sources that can give us real-time information of incidents, as well as kind of any other traffic in nature, like what are the traffic condition in the real time in those locations. So we have done it in such a way that there is kind of the parameters can be used and incorporated in the tool. The current version of the tool does not have this kind of options, but it can be integrated in the tool to make it more dynamic version of the tool.
Thank you, Subasish. Do we have any more? Oh, we've got a question. Can this tool be used for cyclists too?
No, for this tool, we are limited to only vehicular use. So we have no, because for the cycling tool, when we did our literature review, we find that cyclists also sometimes kind of need not only kind of the safety measures in terms of vehicular crash, they also look for kind of air pollution and kind of other whether there is a kind of bike lane versus other non-motorist facility. So we have not incorporated those. That is kind of another future directions for the tool, that when there are non-motorist, how they will use the information, and also we need their kind of air pollution measures, so that they can choose not only based on the risks from vehicular crash, but also risks from kind of air quality.
Thank you, Subasish. Any additional questions from anyone? Okay, if we don't have any more questions, I would like to thank you all for joining the webinar. This webinar will be uploaded to YouTube, and we will notify everyone via email when it is complete. Also, registration is open for our next webinar. The next webinar will be on the safety of ADS systems and how safe is safe enough, presented by researchers at the Virginia Tech Transportation Institute. This webinar is scheduled for January 25th at 2:30 Eastern Time. You can register now with the link provided in the chat. I will go ahead and provide that for you guys now. And if there is nothing else, I want to thank everyone again for participating in the webinar, and we will see you at our next webinar. Thank you.
And I'd like to thank you all.
Yeah, you got it, Subasish. All right. I'm going to go ahead and put that link here. And again, thank you for everyone for joining today.
Thank you.